Hi guys, this is Mr. Robeson with Calculus. We might have a long one today, so I'll try and go quick, but we're going to look at intervals where things are continuous or intervals of continuity. We're going to look at the Squeeze Theorem, which is a fun one, limits of composition functions, which is another somewhat tricky one, and then the Intermediate Value Theorem. All right, so first up, intervals of continuity. So we've got some trig functions here. I know some people don't like trig functions, but really they're fun. They're neat little guys. They're happy little trig functions. All right, so the first one we're looking at here is tangent of x, and we want to describe the intervals where each function is continuous. So in other words, we want to find where it's discontinuous and then say everywhere else is fine. So the way we find where tangent has problems with discontinuity is, well, we could graph it on our calculators if we want, or we can use the trig rule, the ratio that tangent of x is equal to sine of x over cosine of x. And then whenever the bottom is equal to 0, that's going to be where it's discontinuous. So whenever cosine has a problem, that's where tangent's going to have a problem. All right, so I told you earlier we want to memorize the graph of cosine. Cosine starts high, comes down, then goes back up. So there's 2 pi, there's pi. So we've got a 0 right here at pi over 2, and we got a 0 right here at 3 pi over 2. And this will keep going. So we got 1 pi over 2, 3 pi over 2. The next one would be 5 pi over 2. So we're going to say x cannot equal pi over 2, 3 pi over 2, 5 pi over 2, dot, dot, dot. It's just going to keep going. It also goes backwards, and it's going to happen at those negative values too. So this goes really plus or minus pi over 2, plus or minus 3 pi over 2, and plus or minus 5 pi over 2 is where it's discontinuous. So everywhere else it's continuous. So it's continuous everywhere else. All right, otherwise it will just be a smooth curve. All right, the next one. So we've got g of x is sine of 1 over x if x is not equal to 0, and 0 if x is equal to 0. So we took a look at the graph of this guy before, and it was really, really hard to tell what was happening at 0. So it was just kind of going back and forth, and then when it got close to 0, it was just solid line. It was so thick going back and forth, and then it was back out to like a normal type sine curve, and this was going back and forth between 1 and -1. So if we add in this 1.0 here, we're still not really sure what's going on in here. All right, it's going back and forth so fast that the limit doesn't exist. So remember, if the limit doesn't exist, so the limit as x goes to 0 in sine of 1 over x does not exist. We saw the other day because it's oscillating. And the function value, g of 0, is just 0 by definition. All right, but since that limit does not exist, it's not continuous at 0. So it's got a discontinuity at 0, but it should be continuous everywhere else. If we move just a little ways past 0, it's still going up and down, not too fast. Fast, but not too fast. All right, and then that brings us over to this one here, h of x. So we've got x times sine of 1 over x. So I wonder if that times x out front is going to do anything. If x is not equal to 0, and 0 if x is equal to 0. All right, well, it turns out that this x in front helps us. It helps us a lot because that goes to 0. So if we take the limit now as x goes to 0 of x times the sine of 1 over x, this part is going to go to 0. This part is always going to be between -1 and 1. I guess we should probably have an equal to on there. All right, so if we take 0 and we multiply it by any number between -1 and 1, we're actually going to get 0 still. So this limit's going to equal 0. All right, we'll go over this more formally on the next slide with something called the Squeeze Theorem. And the function value is defined to be 0. So the limit is 0, the function value is 0. Those two are both the same, so this guy is continuous. at x equals 0, it's actually going to be continuous everywhere because that's the only spot where we had a problem because we couldn't have 0 on the bottom of the fraction here. So we're continuous from negative infinity to infinity. All right, so what's the squeeze theorem? Well, the squeeze theorem is going to be how we actually take that limit. All right, so here's how the squeeze theorem works. So we take the hard trig part here. So we're taking the limit here as we go to 0. We take the trig part, which is where we're having the problem, because it's the 0 on the bottom of the fraction that gives us the problem. And remember, sign is just, as we go out long, far away, it's just going to keep going back and forth forever and ever and ever. So it's going to be between 1 and negative 1. In fact, here we're squaring it. So if we square it, it will be between 0 and 1. All right, so what we do is we start off by saying, okay, we've got sine squared of 1 over x. That's our trig part. This is always, I'm going to leave some space, less than or equal to 1. And it's always greater than or equal to 0. Because it's squared, it's always going to be positive. Now what we do is we take and we fill in the rest of what's in here. So we've got an x in there, so we're going to say times x. And out here, we're also going to say times x. And out here, we're also going to say times x. Doesn't matter if I put it in front of the 1 or after the 1. Then we're going to take the limit in each part. So then we're going to take the limit as x goes to 0. We're going to do it over here as well. And we're going to do it over here as well. All right, now we're not going to actually work out the middle. This is what we're trying to find. So we're just going to leave this. All right, now over here, x is going to 0. So we have 0 times 0. So this side is 0. Over here, if we plug in 0 for x, it's just a continuous function. That's a line. So as x goes to 0 in that guy, this one also goes to 0. So if both sides go to 0, and it's got to be between these two zeros, that means this guy in the middle also goes to 0. So that means this limit here is 0. That will often happen with this squeeze theorem. Unless there's like a number being added on the back, we'll often end up getting 0. All right, let's try another one of these. We'll switch colors so we don't get them mixed up. Here's one with cosine. So just regular old cosine. We've got x going to 0. We've got x squared times cosine of 1 over x squared. And then we're adding 1 at the end. So as we go to 0, that's a problem right here. All right, 0 on the bottom of a fraction. And cosine graph just looks very similar to sine. Especially as we get out towards infinity, it just starts high and then it's just back and forth forever and ever. So as this goes to 0, this is going towards infinity. So as we go towards infinity, cosine is just bouncing back and forth between negative 1 and 1. So we start with the trig part. So the trig part here is this cosine. So we start by saying that cosine of 1 over x squared is always less than or equal to 1. And the lowest cosine gets to, see how it goes down here, is negative 1. We would have used negative 1 for the sine here too, but, well, we squared the sine, so it was then between 0 was the lowest it was going to get to. Next, we multiply in this x squared everywhere, so times x squared, times x squared, times x squared. And then we've got this plus 1 we want to add everywhere, so plus 1, plus 1, plus 1. All right, so this was a positive 1 in front, so that is plus 1 still. And then we take the limit at each part. So we get the limit as x goes to 0 here, the limit as x goes to 0 in the middle, which we're not going to do anything with, and the limit that x goes to 0 over here on the right. So here we've got 1 minus x squared, essentially. So if we plug in 0, we get 1 minus 0 squared, or 1. Over here we plug in 0, we've got 0 squared plus 1. Right, so we end up getting 1. So both sides go to 1. So that means this limit here, what's left in the middle, will also go to 1. And that's how the squeeze theorem works. All right, you try one. All right, so if you need to, pause the video, take some time and work it out, pick your answer, and then we'll go over it. All right, so let's go over the answer here. So the first thing that I notice is we're going to 0, and we're going to have 0 on the bottom of the fraction here inside of sine. So that guy, that sign, is our problem. All right, so this is sine of 1 over x. It's always less than or equal to 1. It's always greater than or equal to negative 1. Next, it's times x squared. Times x squared. So we multiply every part by x squared. And then we've got plus 2. So we add 2 everywhere also. And then we take the limit in each part. So the limit as x goes to 0. The limit as x goes to 0. And the limit as x goes to 0. So this is probably the easy one here. If we go to 0, this is 0 plus 2. We get that this guy goes to 2. Here we've got 2 minus 0 squared, also going to 2. So if both sides go to 2 and we're between both of them, that means this middle guy also has to go to 2. All right, so our answer here is just 2. All right, next one, composition functions. So if we are composing a continuous function and we're taking limits, then we can actually just plug in the function value for the inside function. All right, and if the outside function is continuous as well, we just plug into both of them. It's really just a consequence of the rule of continuity that the limit is equal to the function value. All right, otherwise we got to check both sides. So here we go, we've got two graphs. They aren't continuous. Well, they're continuous in little sections, like from 1 to 2, from 2 to 3, from -1 to 1, from -3 to -1. F is continuous, but elsewhere we've got jumps. So if we're at a jump, we have a problem. If we're at somewhere in between a jump, we're just fine. All right, so we want the limit as x goes to 2 of g of f of x. So that means we're going to go into f first. So what's happening at f at 2? Oh, we have two different values. Well, that doesn't necessarily mean it does not exist. It just means we have to check both ends. So we have to break this up and say, well, what's the limit as x goes to 2 from the left? Or sorry, I guess that's going to be for the right since I wrote it wrong. And from the other side, that's from the left. So in f, so we'll just look at f here to start. And then we'll take both of those and go into g afterwards. So as we go to 2 in f, bigger than 2, we're down here, so it looks like we're going to -1. Less than 2, we're up here, so it looks like we're going to +1. So now we're going to take each of those as we go to -1 and +1, and we're going to see what's happening in g. So as we go to -1, and again, we're not at -1, we're going to -1. We are at 1. So in g, this guy is going to 1 in g of x. All right. If we look at what +1 is going into, or going towards in g, so 1 for x, looks like we're down here. We're at -1. So those are two different values. So since this is two different values, this does not exist. All right, let's switch colors here and do the next one. So now we're going to +1, and we want f of g, so that means we're going into g first. So as we go to 1 in g, let's see, are we continuous at 1? We are continuous at 1. So it's just going to the function value here, which is -1. So that means this is going to -1. And then we want what's f of -1? Well, f of -1, So now the question is, are we going to -1 or is it exactly -1? Well, we're actually approaching -1 from both sides, but from each side it's a little bit bigger than -1. So from each side, it's -1 from the right, right? Since it's not continuous here. So -1 from the right is a little bit bigger than -1, which would put us up here. So that means as we go to 1, looks like we're going to be up there at 2. This one's a tricky one. All right, since both of the sides here, we went from the left side and from the right side, are a little bit above -1. They'd be up here, so a little bit above -1. We'd say this limit would be just a little bit above -1. For all intents and purposes, it is -1, but it actually would be -0.9999999. So as we go over here, -0.9999 puts us up at this guy at 2, not at 1. Tricky, I know. Next up, let's try this one. We're going to -1 in both of them. So in g, from both sides, we're going towards -1. From both sides, we are going towards 1. So for both of these in G, we're going towards 1. With F at -1, we're going to two different things. So from one side, it's going to 1, and then from the other side, it's going to 2. All right, so it could be 2 times 1, or it could be 1 times 1. So that means this on one side is going to 1 times 1. On the other side, when we put these together, it's going to 2. Since it's going to two different things from each side, this one does not exist. All right, let's check out this last one here. So again, now we're going to 1 in F. So 1 in F. Here's 1. It's two different things from each side, so that's going to have to split up. And G, as we're going to 1, so that would be 1 minus 1, so that would be 0 in here. So that means we're going to 0 on both sides here. So if we split it up, kind of like we did with this last one, but I'll write it out this time. So we got the limit as x goes to 1 from the left of f of x times g of x minus 1. So as we go to 1 from the left, we're a little bit below 1 in f, which is right around there. So we're up at 1. So this will be 1 times, and 1 from the left here, so it'll be 1 minus 1, so it'll be about 0. All right, so again, we'd be right at 0. So this would be 1 times 0. So this one would go to 0. If we look at it from the other side, as x goes to 1 from the right, f of x times g of x minus 1. This is how we do the tough limits, guys. We just break them up into both sides and just check what happens on both sides. So as we go to 1 from the right, in f, where am I? We are a little bit bigger than 1, so we're up here. Oh, where am I? 1, sorry. I did -1 on the last one, didn't I? Didn't matter, because we were at 2 instead of 1, sorry. 2. Yeah, we were over here. I went to -1 instead of 1, so we were up here at 2. Now 1 from the right, we're down here at 0. So we get 0 times, g was continuous, it's still going to be 0. So this one also goes to 0. Since both sides go to 0, we get 0. All right, the intermediate value theorem. One last thing here. So if f is continuous on a closed interval, so in other words, if you can draw it with a nice smooth curve, and k is some number between f of a and f of b, so f of a might be up here and f of b down here, and k is somewhere in between them. We're talking about y values now. Then there is at least one number c between a and b, such that f of c equals k. It basically says if we start up at the top and we end up down at the bottom, somewhere it's going to cross between them. Somewhere it's going to hit that value in between them. That's what the intermediate value is. Remember, intermediate means between. So it's a value between those two endpoints. If we're going the other way around, like if f of a is down here and f of b is up here, and maybe a is here and b is here, that means we have a point here down at a, f of a, and a point up here. If we take any k anywhere we want between them, and we draw some sort of curve between them, it's going to hit k at some point. There, it hit k. That's the c that we're talking about. So it's always going to hit these intermediate values. If we pick a different k up here, it's going to hit it. If we pick all the way up here, almost at f of b, it's still going to hit it. All right? If it's not continuous, then we could have a jump, and then it's not going to work. So if it's not continuous, it doesn't work. So it has to be continuous. That means whenever we use the intermediate value theorem, we have to check to make sure it's continuous, and we have to make sure that k is between f of a and f of b. So we have to look and see, do we have this inequality or the other way around satisfied? So this has to be satisfied and continuous. So number 1, we check, is it continuous? Number 2, we check that. And then we say, okay, then there exists C. We don't even have to find it most of the time. It just exists. All right, so here's our two conditions. So use the intermediate value theorem, which we can often abbreviate IVT on the AP exam. That's one of the abbreviations they take, to show that this function has a 0 between 0 and 1. All right, well, is this continuous? Yeah, it's a polynomial. So since it's a polynomial, and we've said polynomials are continuous, that guy is continuous. Check. So that was condition 1. Condition 2 is 0 between f of 0 and f of 1. Well, the only way to find that is to plug in 0 and then to plug in 1. So if we plug in 0, we get 0 cubed minus 2 times 0, or sorry, plus 2 times 0 minus 1 gives us negative 1. If we plug in 1, we get 1 plus 2 times 1 is 2 minus 1 is 2. So we're negative on one side, positive on the other side. So negative 1 is less than 0 is less than 2. So 0 is between those two endpoints, and this is f of 0, and this is f of 1. So 0 is between them. So by the intermediate value theorem, f of c equals 0 for c in the interval a, b. Or in this case, when I don't have a, b, we have 0, 1. So we're going from 0 to 1. Or you could say for 0 is less than c is less than 1. Right? Those are the two ways we can write that. So that's how the IVT works. Intermediate value theorem, we check continuous, we check both endpoints, then we say by IVT, this is true. There is going to be a point between there. All right, and there it is. There's the graph if you wanted to see it. So, yep, we're up at 2 here at 1. We're down at negative 1 here. So somewhere between these two values, to get between those 2 points, we have to cross the x-axis, and we do right there. All right, so here we go. In which interval does the intermediate value theorem guarantee that this has a 0? It is a little bit of work, but you just got to plug in all the endpoints and see where does it change from positive to negative, or where does it change from negative to positive. Go ahead and stop the video and see if you can find it. Okay, so hopefully you found it. I'm just going to start plugging in at negative 3 and see what happens. So that's going to be negative 27, and that's going to be plus 9 plus 4. This is going to be negative. I didn't even find out what it is. It's just negative. Negative 2, we're going to get negative 8 plus 6 plus 4. Yeah, that's positive 2. All right, so we probably should say what this is. This is 13. Negative 27 plus 13 is negative 14. Yep. So it's negative to positive right here. So we have a sign change. And the function is continuous since it was a polynomial. So that means the answer is going to just be that first interval. Somewhere between negative 3 and 2 is going to have a sign change. If we plugged in all the other ones, like these would still be positive, this would all be positive, this would all be positive. They wouldn't change signs. All right, so I know that was a long one, a lot of stuff there. We have continuity, we went over the Squeeze Theorem, which may or may not show up on the AP exam. We went over the limits of composition functions and doing the one-sided limits, which is really tricky or can get really tricky. And the Intermediate Value Theorem, which they love on the AP exam. It's almost always there. You remember to check continuous, check both endpoints, and then make your statement. All right. And that's it for 1.4. So check on the Google Classroom for homework.